Hello, my name is Julio and I will present you in this session the question answering system on clinical guidelines using Spark NLP. I work for Jon Snow Labs as a senior data scientist. This presentation is about a proof of concept that we have developed for Kaiser Permanente, that is a big healthcare organization in the US. First of all, I will describe you what is the problem description from the perspective of natural language processing. Basically, the problem that we try to solve here is that this company, this organization, had a bunch of thousands of documents that includes information of about how to treat patients or how to approach the care of patients. They wanted a system that allowed the users, clinicians, and other members of the team to make queries in natural language and identify which documents and pieces of sections of those documents were relevant for answering the specific question from the user. In this case, for example, we can have like this bunch of documents in orange, in different formats, PDFs, PowerPoints, DOCX, or whatever format that we are able to process. The user can make a query like how to treat diabetes, and the system will automatically identify those documents and sections of those documents that contains the relevant answer to the user question. So this is what we wanted to achieve, and I will explain you how can you achieve this kind of system using Spark NLP and the Spark machine learning libraries. So it's what we have seen. Given a user information need, express it as a natural language question and a set of documents. We need to identify the passages in those documents that most probably can answer the user question. So basically, in question answering problems, you have like two big paradigms here. You have on the left side, you have a kind of information retrieval question answering approach, where you first need to understand the question from the user in natural language. Then you need to identify the documents that potentially contain the answer to the question. Then once you have done that, you need to specifically identify the passages or the pieces of that document that contains the answer to the question, and then you need to process the answer and show to the user in a relevant and meaningful way. And on the right, you have another paradigm that is the knowledge-based approach for question answering, where you first will you need to understand the question expressed in natural language. Then you will transform this question in a kind of structured query format like SparkQL or SQL, and then you will run this structured query against a kind of a structured knowledge database that you have generated previously from documents or other sources of knowledge. And then once you have done that, you need to process the answer to show to the user in a way that the user finds easy to understand. In addition, when you are talking about question answering, you always will have this kind of closeness or openness domain dilemma. We talk about the closest domain question answering when, for example, in terms of the domain, we will just answer questions related with a specific domain, like healthcare domain or organization knowledge domain, as it was our case. Or you can also talk about a closet or openness in terms of the question, and then you can close the kind of questions that your system will be able to answer to some kind of predefined types of questions, like give me a list of things, give me a yes/no answer to a question, or I will answer questions related with what is called factoids, like where something happened, what happened, who or when. Or you can have an open domain question answering system where you will identify like two approaches here. The reading comprehension based, where basically the system will read a passage of text of natural language, and if the answer is contained specifically explicitly in the source, in the content, you will identify where that answer is located. So it's somehow like highlighting the answer in a given content. Or you can make an approach called open book based approach, where even if the answer is not explicitly directly specified in the content, you will be able to answer the question by picking different pieces of information from different parts of the document, for example. In our prototype approach, what we did is open question. Any question can be answered. The user is not limited to a closed set of questions, but can make any question to the system, but in a closed domain. We will only process and use information included in the set of documents from Kaiser Permanente. We were using an approach based on information retrieval, so we need the answer to be explicitly expressed in a document or a piece of the document, and is, as we have seen before, is reading comprehension based. But we will leverage language models, so even if the answer is not specifically with the same exact words expressed, we will be able to capture that by synonymia and capturing the semantic meaning through the use of these language models. And of course, as we are not talking about an academic approach, but we were talking about a business need, we needed to develop this system at a reasonable cost and time. So we were using pragmatic approaches. I will show you now an brief overview of the architecture of the system, so you can understand the general architecture. Basically, on the bottom of the architecture, we will use Apache Spark that has the advantage that you can parallelize all the processing. So it will scale very well for thousands or hundreds of thousands of documents. And we are using TensorFlow models. On top of that, we have a Spark OCR, that is a library from Jon Snow Labs that is able to extract information from scanned documents, PDFs, or other kind of poorly structured documents. We will use, of course, a Spark NLP, that is this library that on top of Spark from Jon Snow Lab that is able to process natural language in a very convenient way. And on top of that, the Spark NLP, we will be very focused specifically in a new, recently released in the last year. We recently released this kind of BERT models that are trained at the level of the sentence. And specifically, we will use a sentence BERT model that is specifically trained to understand or to capture the semantic meaning of biomedical content. And in parallel, we will use Spark machine learning library, the open source Spark library. And specifically, we will be using this bucket random projection LSH annotator that is able to cluster and to improve the performance of the system, as we will see later. About the data flow of the whole system, how is the data going through the system? We will see now. This is an overall view of the data flow. Here on the top left, you have the documents, the original documents. There were like hundreds of thousands of documents. So the first step is we need to extract that the content of those documents. Some of them were scanned documents, PDFs, DOCX, PPTX, HTML pages. So first of all, you need to extract that information, extract as a binary content in some cases, and transform through Spark OCR into text content, where each row will contain one page of the original documents. Once you have that, you will transform with the help of the Spark NLP, and then you will represent every sentence of those documents as a set of embeddings, a list of float numbers based on pre-trained language models, specifically pre-trained for dealing with biomedical content. Once you have these sentences semantically represented by embeddings, by BioBERT embeddings, we will use this random bucket projection to get to a couple of things. You will keep that embeddings from the sentences, but you will have like a kind of index in the form of buckets or hash functions that will help you to identify quickly which other sentences are similar to your target sentence in a very convenient and fast way. Let's talk now about the question of the sentence embeddings. This is this part of the data flow up to embeddings. So here is in detail the code, an example of the kind of code that we were using. On the top you have like a reference of the pipeline. Here you have the original content, the Spark OCR as a whole pipeline that will generate, will extract from the binary content or multi-format content, will normalize and extract the text. So you can then apply a Spark NLP to get the sentence embeddings. And you see here the smallest pieces of the pipeline. So you will start, of course, importing all the needed libraries. You will import the Spark NLP, you will import the Spark OCR, basically. You will start the Spark session here. In this case, we are using a license session because we are using this specific BioBERT sentence BioBERT model that is licensed. But if you don't have the license, you can use other open source pre-trained models. They will not work so well for biomedical content, but you can try. And then you have the definition of the pipeline here. You see, like the first step is we are using this PDF to image transformer. So we will get the binary content, and then we will output a new column with the image. Then we will use this other component that will transform the image into text. So the input column is image and the output column is text. Once we have the text, we need to wrap the text into a kind of data schema that is called a document assembler. With the document assembler, we will get the text and we will generate this document data schema. And once you have this document data schema, the first step is we need to split the content from the document, the original document, into sentences. And here we will use a deep learning based model that is able to identify sentences. The name of this pre-trained model that is open source is Sentence Detector DL from deep learning. And it basically will take all the content of the document and will generate this the sentence split. And every row will now contain a different sentence. So once you have the sentence split, you need to apply to extract the semantic representation of that sentence with some embeddings, with a list of values. This is what we are doing here with this BERT sentence embeddings model, that in this specific case, we use this SBioBERT based case MLI model that is pre-trained and is a licensed model, but there's plenty of open source models you can try here. So you will get the sentence as an input and you will get as an output the embeddings. Here we are stating the stages of our pipeline. All these components are put together into a pipeline, and then we are fitting the pipeline to be ready to process whatever content we give. And here we are basically reading as binaries all the PDFs, in this case, all the PDFs located in this specific folder that we are specifying here with this URI. So when you transform as a last step, you transform using the fitted pipeline that is called here model. You transform whatever content you have extracted and loaded into the Spark data frame. You will get the results. You will get the embeddings. You will be adding different columns, and at the end you will have this embeddings column. Here is an example of the difference between the traditional token embeddings from BERT and the newer sentence embeddings that has been released. So, for example, in the traditional by token embeddings, you will have a sentence like hypertension is the most important risk factor for stroke, for example. And what you will do is you will tokenize, you will split the sentence in different words or tokens, and you will get by using this pre-trained language model, you will get the representation of every word or every token by this list of float numbers. Every word we have a different representation. If you want to represent overall the semantic meaning of this sentence, something that you usually did in the past was, okay, I will average all the embeddings, so I will get an average representation of all the tokens. In the new approach, you directly are training the language model to represent sentences. So directly you will get, with the sentence embeddings models, you will get a semantic representation of the whole sentence directly without averaging. It's slightly better than averaging this approach. So you will have the representation of every sentence in the documents as a list of float numbers, in this case 786 numbers. Once you have that, an interesting thing that you can find is that those sentences that are closer in meaning will tend to have to be closer in the distance of their embeddings of their representation will be closer as closer is the meaning of the sentence. So for example, with a couple of sentences like controlled hypertension reduces the risk of cerebrovascular accidents, or hypertension is the most important risk factor for stroke. As those sentences are similar in meaning, you will see that they will tend to have this, in this case, cosine distance very small. And then you have other sentences like around 10% of US population suffers from diabetes, or the prevalence of diabetes in Canada is 9.3%. As those couple of sentences is very similar, you will have they will be closer or close in terms of cosine similarity. So you can leverage that to group sentences by meaning. The problem with this is that you will have like millions, literally in this use case, you will have millions of sentences. So you need a method to speed up the search of similar sentences within those millions. You are not interested in comparing my target sentence with millions of sentences. That will take too much time. But I want a way of reducing that the time that I need to find the closest sentences. This is why we use this random bucket projection. That will give us a way of getting a nearest neighbor, but not an exact nearest neighbor. That could take a lot of time and will scale poorly. But you will get an approximate nearest neighbor that has the characteristic of being very fast and scaling very well. This is what we explain now as the next part of the pipeline, this random bucket projection. So the underlying idea of the system in general is that once you have pre-calculated the sentence BERT representation for all the sentences in the corpus, you will receive a new question from the user. Using the same language model, you can get the sentence representation of the user question, of the user query. So basically, the next step is, okay, I have this user query, and I want to get the closest the sentence in the corpus that are closer to the question of the user. So those will be good candidates, and the context where those sentences are located within the documents will be good candidates to contain the answer to the question. But as we have seen, if you have this question from the user in red, and you want to compare the distance between all the millions of sentences that you have previously extracted the embeddings of, it will take too much time, basically. And you need an answer in less than 1 second, let's say. So just a reminder, you can have like two kinds of distances calculated. The one on the left is the Euclidean distance, is the typical one. And on the right, you have the cosine distance. That is similar to the Euclidean system in terms of results, but you are not calculated the linear distance, but you are calculated the angle distance, okay? BERT is trained for cosine distance, so usually you will get better results with cosine distance, as we have used it here. So how does random bucket projection works in practice? So let's imagine you have like a set of sentences with represented by embeddings, and you are plotting that in the left here. So you can basically generate a random vector with the same dimensionality than the sentence embeddings that you are using. In our case, is 768, but we are illustrating with just 2 dimensions to understand better. So you do this in such a way that when you identify a random, or you draw a random vector here in orange, you will split the whole space, the whole semantic space in two areas. So those sentences that are in this area here on the right up, the right section, we will tag as ones, and those that are on the left we will tag as zeros. So basically we have used this random vector to represent all the elements, all the entities in a binary way. We can repeat the same approach with adding a new vector now in blue, and so now every entity will be represented by 2 binary numbers, 1 or 2 or 0, depending of in which side of the random vectors those entities are. So now we are representing every entity with 2 binary numbers, a hash of 2 values, let's say. We can repeat this again and again and have a third random vector, and we will get this all the entities represented by 3 numbers, or all the entities being grouped in buckets represented by a hash of 3 values. At the end, what you will get here is that you can group together those entities that are closer. They will tend to fall into the same what we call bucket. They will have the same hash representation. You see here that these 2 sentences here that whose cosine distance is very close are falling into the same buckets, and this one is falling in the different bucket, the bucket 0, 1, 1, and these 2 ones are bucket 0, 0, 0, and are together because they have a very low cosine distance. So those buckets with low cosine distance will tend to have the same hash representation, and this is a kind of index. So once you have a query from the user, you of course you will store that hash function that is representing the entities into a hash, into a reduced index. And once you have the question from the user, you basically will get the embeddings that we have seen, and then you will apply this hash function to get the buckets or the hash representation of those embeddings that is much more reduced. You can see here that we are representing this red query with just three numbers. So you can do in a very efficient way. You can say, okay, now I will calculate the distance, but not for the whole sentences that in the corpus, but only for those sentences that are falling into the same bucket, that are probably the most the sentence more, with a higher semantic similarity. So we are reducing the number of calculations we need to do. Of course, if that is the case, that the user makes a query and that query doesn't, the bucket of that query doesn't have has enough examples of other sentences, you can always expand the query to the close to other close buckets. And calculating the closed buckets or the closer buckets is very efficient, because you can basically apply this Hamming distance, where you will say, okay, between this bucket here of 1, 0, 0 and this bucket here represented by 0, 0, 0, how many bits of information are different? It's 1. So you, and in this case, in the second case, is 1, 0, 0 compared with 0, 0, 1. If we do the Hamming distance, you will get number 2. This is a very quick calculation, because it's based in binary comparations. So you will get quickly that the closer buckets here are this one and this one here, and then you can expand the query of trying to find the closest sentences to the buckets that are closer to the original bucket of the query of the user. This is an example of how this works in terms of Python code. So you will have this, you need to import this bucket random projection annotator and this bucket random projection model that is included in Spark ML library, in this case PySpark.ml. And then you will basically get this class, an instance of this class. You need to identify what is the input column, what is the name of the output column that you want. Usually you will use hashes. And then you will need to specify the average length of the bucket that you want and the number of hash tables you want to use to represent this reduced index of the embeddings. Basically, you will get the results from the whole, all the embeddings from your corpus, from all the documents, and then you will feed this bucket random projection LSH to get a random bucket random projection model. This is what we are doing here. So with that, you can basically use this model fitted with results df with all the embeddings. You will use that to transform this the same embeddings, sentence embeddings. So at the end, you will have for every sentence that had an original sentence embeddings representation with 783 float numbers, you will have this reduced representation by in the form of hashes that allows you to say, okay, this sentence and this sentence belongs to this bucket or this other buckets. So once you have this, you have trained this bucket random projection model, how do you get the nearest neighbor for a new user query? We will see that in gray, we are using this, we can call this as a preprocessing step. We are now reducing here a preprocessing step with all the extraction of the OCR extraction, embedding sentence splitting, tokenization, embeddings representation, and random buckets projection. So we will have this for the whole documents, and we will get this embedding content representation for the whole, all the sentences from the corpus, and you will have these bucket hashes tables that allows you to convert any embeddings into a hash representation. For a new query of the user, you will apply the same pre-processing steps. So you will get the sentence embedding of that specific question from the user. And then once you have that, combine it with the bucket hashes Spark data frame, that is at the end of the day is the index, you can apply this approximate neighbors method from the random bucket projection model. And then you will get automatically the K similar sentence list. You can set up here for the 5 most similar sentences or 10 most similar sentences. This is what we are doing here in this code. We are doing the preprocessing part. We are getting the content of the user, wrapping that content into this document assembler, in this document data schema, that then we can use to split in case that the user is adding more than one sentence. But usually we expect to have just one query is one sentence, and then we will extract the sentence representation of the user query. Once we have that, we need to feed that pipeline, and then we will use a light pipeline that is a specific component from Spark NLP that allows you to run these inferences in natural language pipelines without the need of starting all the Spark session. Is much faster for processing small pieces of text. So here we are using this light pipeline model, the light pipeline, and we are transforming with the light pipeline the specific query from the user, how to treat diabetes, and we are extracting the embeddings. And this is why we get this. We get an embedding representation based on sentence bio-BERT embeddings of the user, of the question of the user. So once we have that, the query embeddings here, we will use the bucket random projection model that we previously fitted and persisted, and we will use the approximate nearest neighbors method from this model. And we'll ask this this method to give us the four most closest sentences to the user query in our original documents. And you will get these sentences. This is a real example. What are the treatment for diabetes? Who needs the diabetes medicines? What are the medicines for diabetes 2, for type 2 diabetes? And what causes type 2 diabetes? In this case, this is a false positive. But in most of cases, you will get a good result, and you will get the distance here. So you can even apply some thresholds to say, okay, I didn't find any sentence that is really close to your query in that case. This is what we are doing here as a reminder. So once you have that, as you will save, of course, the reference of that sentence in which document and which page and in which part in the sequence of the sentences of the corpus, of course, you will always keep in that information in your data frame. With this approach, you can base it on a query from the user, like how is the treatment or how to treat diabetes. You will get these 4 sentences, and then you will be able to give to the user the sentence with the context where those sentences appeared in the original corpus. So probably the user will get this information that will contain the answer to the user query. And that's all. Any questions, suggestions? I'm free, and I'm happy to answer or contact you later. Thank you very much.